So therefore, in this session, so we will take a translational systems. Translational systems. So now here we are going to consider a basic mechanical system which consists of one spring, one mass and one dashpot, which is called as mass spring dashpot system. So therefore now consider a translational system which has a spring, one friction element and then a mass. So force F is applied. Because of that there is a displacement x, k is the spring constant and b is the friction constant. Okay, so such a system is called as mass spring dashpot system. Now in order to analyze this system, we have to first write its free body diagram. Okay. So in the free body diagram, we are representing again the elements involved in the system, that is mass is there, as well as all the forces that are acting, that is k into x, and here this will be b into dx by dt, force F. So because of that the resulting displacement x. So this diagram is known as a free body diagram. Now once the free body diagram is drawn, okay, so it is possible to further write the equation for this system using Newton's laws of motion, which is called as the force equation. So for such a translational system consisting of one mass element, one spring and one dashpot element where force F is applied and there is a single displacement x. Okay, so the force equation is given by F is equal to, the first element is mass. So we know from the previous discussion that, okay, so F, whenever force F is applied, then for the mass, so the equation will be m into d square x by dt square. Okay, if only one mass is there, then we would have written only this equation. Now this is a complete system which has both, which has all the elements, like spring is also there, friction is also there. Okay, so mass is also there. So therefore total force F is equal to, first is the mass element equation plus, next we will take the friction component, that is b into dx by dt, plus last one is the spring constant, that is k into x. So this equation represents, take it as equation 1, it represents a linear constant coefficient differential equation of second order. Linear constant coefficient differential equation of second order. Second order because it is highest power is 2 here. Okay, so therefore this equation 1, it represents the distribution of the force, that is F is equal to, first the mass component, how it responds to the applied force, then friction component, then the spring component. So in the previous session, while discussing the elements of the translation system, we have individually seen, that is whenever you have a mass element with the applied force F, then what is its equation? Force balance equation. Similarly, when there is a single damper system or a friction system, so then the force equation will be b into dx by dt, assuming that only one side is displaced. Similarly, when we have a single spring, okay, which is displaced at only one end, then its force balance equation will be F equal to K into X. Okay, they were for the individual elements. Now we are considering a whole system. So which consists of, okay, many masses, which may consist of many spring constants or many friction elements also. Okay, in this system, it's a very basic system. Okay, so which has one mass, one friction element, and one spring element. So for such a system, this is the very basic force equation. Okay, and in this, the mass and the spring, they represent the storage elements. They represent the storage elements, because mass is going to store the kinetic energy, whereas the spring is going to store the potential energy. And whatever this frictional constant is there, B, so this is a dissipative element. Okay, so in the form of heat, energy will be dissipated through the friction. Okay, so if the friction is more, dissipation will be still more. Okay, so therefore in this basic system, okay, so mass and the spring, they represent the storage elements, and the friction B represents the dissipative element. Okay, so finally equation 1 is a force equation used to represent the translational system. Now further, if your system gets complicated, like if you have some two masses, two spring constants, and three frictions or two frictions, then we will extend equation 1 only. Okay, so in order to match the given system, that we will see in the later sessions. So today we are considering only the basic systems for translational as well as for the rotational systems. Okay, so now similarly we will go for the rotational system. So in case of rotational systems, how to represent the torque equation. Okay, so therefore next I am writing rotational system. Okay. Now in case of rotational system, you just recall what are the elements. Elements are mass of inertia, and then there is a friction, as well as the stiffness is also there. But now in case of rotational systems, so the mass of inertia is represented by a rotating disk, as well as the springing effect is represented by the stiffness of the shaft. Okay, and whatever the friction is associated with that disk, okay, so that is represented by the viscous friction, that is element B. So therefore a rotational system is represented as shown here. So here you have the shaft element, so and surrounding this we have the disk. So I am drawing the disk now. So this is the disk. To the disk, the shaft is attached. Okay. So therefore here, whenever it is rotating, okay, uh, the friction B is associated with this. Then what we need to apply is the torque T. Torque T is applied here. Okay. So because of that, we observe theta, which is nothing but the rotation. So what is this? This is the disk element. This is the disk which represents our mass of inertia. So now this is the shaft. Shaft stiffness. Okay. So just like our translational system, so this is also a simple rotational system having one mass of inertia, which is represented by the disk, nothing but J it is. Then there is a shaft which represents the spring, and there is a friction So which is again represented by the P. So friction will be associated with this mass of inertia. And here we are applying the torque T. So this is the torque which is going to make the disc to rotate. So when it starts rotating, the disc will exhibit angular displacement. Okay, so angular displacement will lead to angular velocity. Angular velocity is going to lead further to angular acceleration. Okay, so this is what is the basic corresponding to the rotational element. So next we are going to write a free body diagram. So in the free body diagram, so we are representing a shaft like this, and this will be attached with the J. So the torque T is applied. Because of this, the shaft stiffness, that is springing effect, that is K into theta, and similarly the disk is also associated with B into d theta by dt. Okay, so now using this equation, now we have to obtain the torque equation. Okay, so therefore the torque equation is written like this. Applied torque T will be equal to, now anybody, yes, anyone can say what is the torque equation? Just comparing with the previous force equation, what will be the first term here? Huh? What might be the first term? J
J
into, yes. Next,
d square theta by
next,
dt square.
dt square. Next is what?
B into d theta by dt.
Dt. Yes. Next,
Plus k theta.
K into theta. Okay.
Theta.
So this is what is our second equation. So now F equation, that is force equation and torque equation. So they are the standard equations representing translational system and rotational system. Still we are in mechanical system part only. Okay, so next we are going to take up our electrical system, and later we are going to compare how a mechanical system elements can be compared with the electrical system elements. Okay, so therefore to complete this part, this is what is our torque equation. It shows that how applied torque will be distributed to these elements. So the first part represents what? The opposing force given by the disk element. Second part is the friction because of the movement of the particular disk, and third will be the disk will be always attached to some shaft. Okay, so therefore the shaft has stiffness, so but still it tries to rotate. Okay, so therefore that stiffness of the shaft, it is just like a spring. Okay, so that will be represented by K into theta. So overall the applied torque T will be equal to sum of these three forces, or the torques you can say. Okay, so therefore now to summarize, uh, just so we have now for translational system